Hello there. In this video, we're going to be looking at error types and hypothesis testing. So no matter what the conclusion of a hypothesis test is, neither of the hypotheses are actually proven. So if we fail to reject a null hypothesis, we cannot say that the null hypothesis is supported. We can only say that the evidence does not support the alternative hypothesis. Now, many of you may be wondering, well, why is that the case? The only thing that establishes a true cause and effect relationship or proves anything is an experiment. And so without the experiment, we can't make a definitive conclusion. So you might be wondering then, well, what's the point of a hypothesis test? Well, a hypothesis test can certainly help avoid having to go through all of the steps of an experiment if we in fact figure out that our alternative hypothesis is not supported anyway. So it helps to cut out a little bit of that work for us. Now, inadvertently, when we do a hypothesis test, we can make some errors. And I don't mean computational errors, but these are errors that just come up naturally because there is some chance that we may have made a mistake. And so the first mistake we can make is to reject a true null hypothesis. This is called a type 1 error. Remember that the wording here that's highlighted in yellow would be filled in the blank in your guided notes. The second error we can make is failing to reject a false null hypothesis. This is known as a type 2 error. And to help us with figuring out whether or not we've made a type 1 or a type 2 error, the text has provided us with this useful table that is found on your formula sheet and will be available for you on your exam to help us to determine whether or not we've actually made the error or potentially a correct decision. And so what you do is you look for your decision on the left side. You either rejected the null or failed to reject, and then you look at what reality was in the top row, which either being the null is true or it's false, and then where the two intersect let you know whether you've made a correct decision or the specific error. The decision criteria that we use in a hypothesis test is usually based on the idea of minimizing a type 1 error. That's what we try to do. So the probability of rejecting or making this type 1 error we call alpha. And that is, of course, the level of significance that we talked about in the previous video. So the smaller the level of significance, or in other words, the smaller the level of alpha, the more evidence required to reject the null hypothesis. And in many ways, we like to pick alpha to be small. Okay, because what we say then is that we have a stronger test, there's more evidence that's needed, and so that sometimes is better, but you do have to be careful not to make it too small. Further, there's an additional caution because if you look at alpha being the probability of making a type 1 error and beta being the probability of making a type 2 error, we do have this balance where one affects the other. So the smaller the probability of making a type 1 error, the larger the probability of making a type 2 error will be. So you have to be careful to pick alpha to be small to control the type 1 error, but not making it too small where it's impossible to get enough evidence to reject the null. So what we're going to look at next are some examples, really just two examples, where we're given a context and they ask us whether or not there's been an error. So what I would encourage you to do is pause the video, read this example, and write out what the hypothesis is, and I'll take it from there. Okay, hopefully you've had an opportunity to read through this problem and write out what the hypotheses are. If you read closely, what you should notice here is that we're dealing with means, and so the hypotheses are going to be using mu. And if you read even closely, you'll see that the alternative here was that the insurance company was thinking that the mean is more than 1,000 miles per month. So that's why the alternative is mu is greater than. And then, of course, the null, the status quo, carries the equal sign. Now, the decision that we're given in this case was that they rejected the null. So what this means is the null is wrong. Okay, that's how I think about this. So that put another way, the alternative supported. So in other words, the amount of miles we have driven is more than 1,000. Okay, well, what was reality? What did they find? Well, in reality, they found that people are driving 1,250 miles per month. Well, that's more than 1,000, isn't it? Doesn't that support the alternative? Isn't that what we agreed to when we rejected the null? So since that's the case, we actually have a correct decision here. They didn't make a mistake. Okay, so they rejected the null, which means they're supporting the alternative. The number of miles driven is more than 1,000, while in reality it was. So there's no incorrect decision here. Everything is correct. Now here's the next example. So I would encourage you again to pause the video and give this one a try, maybe all the way through. See if you can figure out whether or not an error has been made. Okay, in this particular example, we are once again dealing with averages. So we're looking at mu here. And you'll notice that this is a two-tailed test because Kiko believes that the number of hours kids are watching TV per night is not 4. So that means it's not equal to 4. Now, she does this hypothesis test, and the decision she comes to is rejects the null. This means, just like in the other example, we're supporting the alternative. So that is the kids are watching not 4 hours of TV. So maybe it's more, maybe it's less. Okay. So there's some difference. It's just not 4. Well, what was reality? Reality was that the kids are watching 4 hours of TV per night. Uh oh. Okay. Kiko has made an error here. Okay. She rejected the null, which was the mu is 4. Well, reality was it was 4. So there's a mismatch here. There is a mistake. So what kind of error did she make? Well, because she rejected a true null hypothesis, this is a type 1 error. Now, what we're going to move into next, now that the error types questions are settled, is actually how to conduct a full hypothesis test. Now, let me preface this by saying that I use 5 steps to complete hypothesis tests in my class. You may take other instructors who do this differently. Just keep this in mind as you move forward, especially through future statistics courses. So, the first step to any hypothesis test is to state the null and alternative hypotheses. And so remember, you have to make a decision of whether or not you're dealing with means or proportions and use the correct variables. Step number 2 is to compute the test statistic. Remember, that is the fancy name for z-score. So you're going to be using some chapter 7 techniques. Step 3 is to find the p-value, which remember is the probability that we get a sample. So you're going to have to use your normal table based on your z-score or your test statistic found in step 2. In step 4, you need to make a decision regarding the null hypothesis. And so, how do you do that? Well, you compare the p value, your probability that you found in step 3, against the given level of alpha. So, remember, alpha is the level of significance or the probability we make a type 1 error. Okay, so alpha has to be given to you ahead of time. All right, so look for that in the problem. And step 5 is we state the conclusion of the hypothesis test by simply answering the question that's posed in the problem. So let's see how all of this works, okay, from start to finish. So what I would encourage you to do is pause the video, read this problem, and then I'll walk you through the steps. Okay, hopefully you've had an opportunity to read through this problem. So the first step to this is to state the hypotheses. And so the first thing to really look for here is this dealing with means or proportions? Now, if you read this carefully, you don't see the word average, you don't see the word mean anywhere. So our conclusion is that we're dealing with proportions. Now, this is further clarified in the second to last sentence when it says of the 50 subjects 29 choose fresh brew. That is in fact a proportion. Okay, 29 out of 50, and that's going to come back to us in a moment. So we're dealing with proportions, so we use p. Now what's interesting enough here is many people will wonder, why is it 0.5? What is he doing here? Well, you're dealing with a proportion, remember, a percentage. And so if the proportion is 50%, that means that the other proportion has to be 50%. Okay, they're evenly matched. Okay, so thinking which proportion of coffee drinkers can tell the difference or can't is 50% either way. That's the status quo number. And so if we're over this 50%, that's what we're looking for, or if we're under, then that's what we're also looking for. Now in the alternative case here, it says in the problem that we believe the proportion is more, so that's why we're looking at greater than. Now, step number 2 is that we need to compute our test statistic, which remember is a z-score. So what we have to look at, if you look at the very last line, is the probability that p hat is greater than 0.58. Okay, so where am I getting 0.58? Well, that's coming from the 29 out of the 50 who have chosen fresh brewed coffee. That's where that's coming from. Okay, based on our sample. So if somebody took another sample, they would get a different p hat potentially. Okay. Now, the other question people ask is, why is it greater than? Why am I looking at p hat as greater than? Well, to answer that, I need to go back for a moment, and I'm going to draw your attention to the alternative hypothesis. Look at the inequality. What's the inequality? Hopefully, you see that it's greater than. So, because the alternative is greater than, and that's the claim that I'm looking to test, my test statistic also has to follow the same. So, if that had been less than in the alternative hypothesis, well, this would also be less than. Now, if you're paying attention more carefully and you say, well, what about if it was two-sided? What if it was not equal to? Well, for that, you have to watch the next video. So I'll leave you with a little cliffhanger there. Okay, so to figure out the probability that p hat is greater than 0.58, we use our chapter 7. So we use central limit theorem. So we take the probability that z is greater than, and we take the sample statistic, 0.58, subtract the parameter, which is zero point 0.5, and then we divide by the standard deviation for the sampling distribution, and that work is above with the big square root. S is equal to, hopefully that looks familiar, 0.0707. Simplify all of that fun stuff, and we get the probability that z is greater than 1.13. So just to be clear, 1.13 is the test statistic. That's your z-score. So in step 3, getting ahead of myself, we had to figure out the p-value. So to do that, we go to the normal table. So just to remind you, we're looking for z is greater than 1.13. That's area to the right. So what I chose to do was look up 1.13, and that gives me a value of 0.8643. I subtract that from 1, and I get 0.1357. You could have also looked up negative 1.13. And receive the same answer. So remember, you have that option for area to the right. So anyway, our probability that our sample, this particular sample, occurs is 0.1357. That's our p-value. That's our probability. The question is it rare enough? To do that, we have to make a decision. We have to compare it to the level of alpha. So alpha, okay, is going to be 0.05. That's typical convention that's used. So you compare the p-value. What you should notice is the 0.1357, it's more than 0.05. That's not significant. In order for it to be significant, we would need it to be less than alpha. That's how we know this sample is rare enough. This one isn't, unfortunately. So the decision here is to fail to reject the null. So once again, we needed p-value to be less than alpha. We didn't get it here. Wasn't a good enough sample. So that's the decision, fail to reject the null. So the conclusion then is, well, at the 0.05 level of significance, there's not enough evidence to say that more people prefer fresh brewed coffee over instant brew coffee. And notice we always begin the conclusion with a statement of what the level of significance is. So to my students, I'm looking for that. Make sure you write that at the alpha equals 0.05 level of significance. And then you say whether or not there is or isn't enough evidence. In this case, we don't have enough evidence, unfortunately. So this is a fully worked hypothesis test. In the next video, we're going to be working some other examples.